So, good morning, everyone. Myself is Dr. Ajit Kumar, and I'm faculty in the Department of AC in the Presidency University. So, we will start our fifth lecture. That is, we will start our fifth lecture, which is for this 128 byte of RAM organization. So, we'll study that how this total 128 byte of RAM is actually uh, organized in our 8051 microcontroller. Right? So here I will draw just and show you how it is actually divided into 128 byte of. So let's say this is our 8051, okay, RAM. So in RAM, in the RAM in 8051, I know that we have 128 bytes of on-chip RAM, on-chip RAM. So object means suppose this is your 8051 microcontroller. So in that case, okay. So in that case, so 8051 means this is your 8051 IC. Okay. So inside this IC, we have on chip 128 byte of, okay, 128 byte of RAM, 128 bytes of RAM. Okay. So that is the meaning of on chip. So how it is actually organized is here in each location. Okay, in each location, suppose that we have this first location. Okay, then we have this second location. Okay, then we have third location. Then we have fourth location. Then fifth location, sixth location, seventh location, and so on. So one, 2, 3, 4, 5, 6, 7. Let's take one more location. So here in each location, okay, these are called locations, and in each, okay, in each location, 8-bit data can be stored. Okay, in each location, 8-bit data can be stored. Okay, so here 8-bit means there will be 8 different cells. In each cell, 1 bit of data will be stored here. Okay, so for example, let's say 1, 2, 3, 4, 5, 1, 2, 3, 4, and then similarly 1, 2, 1, 2, and then here 3, 4. Total 8 bit can be stored here. This is the meaning of each location storing 8 bit. Right? Now, what is happening? This total 128 byte is there. So I know this 8 bit. Okay, I know that this 8 bit is equals to 1 byte. Okay, 1 byte. So it means that each location can store 1 byte data. Okay, so here our 1 byte data will be there in this location, another 1 byte of data can be stored in this location, another 1 byte of data can be stored, and so on. Right? So like this we can store total. So how many total locations are required if you take from here to here? Okay, so I need 128 locations. to store 128 bytes. Okay, 128 bytes. So I need to 128 locations here. Fine. Now, how they are organized is actually they are organized in different. They have been segmented into different parts. Okay, so we'll see that how they are actually uh, segregated into the different parts. Okay, let us try to understand this. Fine. So we'll do one thing here. What is to be noted is total there are four register bank that we discussed in the last class. Okay, each register bank contains eight locations, or you can say 8 byte storage. Okay, so from here, so from this, okay, that is if I say this 1 byte, 2 byte, okay, 3 byte, 4 byte, 5 byte, 6 byte, 7 byte, 8 byte. Okay, this 8 byte is actually the first 8 byte is actually the called register bank 0. Okay, this is called register bank 0. Register bank 0. Okay, that is the first 8 byte. All these 8 first 8 byte, all these 8 bytes. Okay, they are stored in the register bank 0. Fine, register bank 0. And similarly, the next 8 byte, okay, next 8 byte, suppose that I'm taking here 8 different locations here, okay. So this next 8 byte is called register bank, register bank 1. Similarly, the next 8 byte is called register bank, register bank 2. And similarly, we have another one which is called register bank 3, register bank 3. Fine. Now in each location there are 8 storage, or you can say 8 locations. Okay, in each register bank there are 8 locations. Here also 8 locations. Okay, here also for this also we have 8 locations. Fine, and so on. Here also 8 locations. So those 8 locations are not shown like here in the register bank are shown. Okay. So you try to understand here. So, and when this memory chip is storing something, okay, this data can be required by the microprocessor to access them. Okay, so how the microprocessor will access the data stored in this RAM. Okay, we know that if a postman is supposed to come and deliver or receive letter, so in that case, that postman should know the house number. Okay, otherwise he won't be able to reach our house. Similarly, here also, each location is having their own addresses assigned by the designer. Fine. So here, for each location, we have assigned some address. Okay, now since our address, I mean, we need 128 locations. Okay, 128 locations. Okay, so in that case, see how we can assign the address. Okay, I'm just giving one simple example. Suppose that here we have small memory chip capacity. Okay, let's say this is the small memory chip capacity having 4 locations. So 4 locations means let's say here one divided and then here and then one here. Now try to understand that there are only 4 locations here. Okay, so four locations has to be assigned some addresses. Okay, some address. Now addresses are also assigned in the terms of zeros. Okay, zero and binary one. You know that the microprocessor can understand only 0 and 1, the language machine language. So here we need to assign the address in the terms of zeros and ones. Okay. Now, if I have 4 locations and I can use the combination of 0 and 1, so in that case, you can see This first location I can assign address 00. The next address I can assign 01. Then the next one is 10. Then the next one is 11. By the combination of 2 bits, I can. So here 2 bits. So using 2 bits, I got 2 power 2. That is 4 combination. Okay, 4 combination. So I can assign this. Okay, I mean 2 bit combination for the each location, and I can say that these are the addresses. Okay. Similarly, let's say that I have a more large memory chip. So let's say this is our memory chip having this time not 4 but 8 locations. Okay. So how we can have different locations? Here you can have total how many locations I'll assume is 4. Okay, so let's say this way 4 means so now we need 8 locations. So 8 locations is 4. Then here okay, so this time we have 8 locations. Okay, so this time 8 locations. So to assign addresses to these 8 locations, I need 3 bits. 3 bits means 2 power 3, 8 combinations I can have. Okay, 8 combinations using zeros and ones. Okay, so 8 combinations means 3 bits. No, so let's take the first address 000, and then next address is 001, then next address is 010, then 010, then the next one is 011. Okay. So I'll rewrite the addresses 000, 001, then 010, then 011, that is 0123, then 4 is 100, then 5 is 101, then the 6 is 110, then 7 is 111. So by taking 3 bits, I can have total 8 locations, okay, I mean 8 addresses. These are addresses. So like this, in our case, there are total 128. Here we have 128 locations. Okay, so for 128 locations, how many bit I need? You know, 2 power 5 is 32, 2 power 6 is 64, 2 power 7 is 128. Okay, so if you take 2 power 7, then you will get 128. However, in this case, it means I should take 7 bits, 7 bits. But you will see that here I will take 8 bits instead of 7 bits. I will take 8 bits to assign the addresses here. Okay, so let us see here, and uh, these addresses, okay, were in the binary form. In hexadecimal form, you know that this 0 is written as 0. Okay, basically 0h something else. Okay, I'm not assigned here hexa and binary decimal. Okay, that is decimal and hexadecimal addresses. Here, for the sake of understanding, I'll address based on the addresses. Okay, so this side I'll show you. This side I'll show you the decimal address, and this side I'll show you the hexadecimal address. Fine. Now in the decimal address, let's say this is the 01 address. Okay, 00, sorry. And as I said, I'm going to use 8 bit. So in hexadecimal 00h. 00h means for this 0 we know 1, 2, 3, 4, and this 0 means 1, 2, 3, 4. So I'm using 4 bits to assign the addresses. So similarly, the next address will be 01h. Again, this 01h is basically for this 000, and then 1 is 0001. So again, 4 bits I'm taking. Similarly, the next address will be 02h. Okay, that is 0000, and then 2 is 0010. So like this, I'll assign the different addresses 00, then 01, then 02 for this. Then for this, it is 03. Then for this, it is 04. Then for this location, 05. Then the next location, 06. Then the next location is 07. So you can see from I'm starting from 0, then 01, 2, 3, 4, 5, and here I'm taking 07 is the last location. This side I'm showing you the decimal number system. Okay, this side decimal number system. So the next, and now this is another register bank. Okay, register bank 1, having again 8 locations which are not shown here like this. Okay, so 8 locations means we have here it will start from 08. Okay, then 08 is the starting location and it can store 8 bytes, so it is 16, but it will not go to 16 but it will go to 15. Now what is the this side? This side in hexadecimal it is 08 only. Okay, then 09, then 08, 0B, 0C, and this 15 equivalent is 0F. Okay, so this side it will start from 08, will go to 0F. Now similarly we have another register bank 2 whose another location, I mean we have 8 locations. So the starting address will be after 15 in the decimal comes 16. Okay, so 16 equivalent in hexadecimal is, this 16 is the decimal number. So in hexadecimal it will be 10. How? See, divide this 16 by 16. 16 one the 16, and then remainder is 0. So this is quotient, this is remainder. So QR is 10. So in that case, you will write this 16 as 10 in hexadecimal. Similarly, the next address is 17. Okay, so we'll do one thing. Here it is getting uh, this. So I'll draw a larger one. So there is no table form something here. We could have no issue. So let us take this simple case. So that is, uh, so I was saying that let's say this is our memory chip, or just to I'll do one thing. Here we have already drawn this diagram. Okay. So see here now 00. So you can see this 00. So this 00 is the first address. Okay, then 01 is the next address, 02, 03, and like this. 7 address, total 8 locations, 8 locations, 8 addresses. Similarly, we have another 8 locations here, 1, 2, 3, 4, 5, 6, 7, 8. For each locations, we have address 80809. Then after 9 comes A in hexadecimal. So 0A will be there. Okay, 8. Okay, I'll write here 09, then 0A, then 0B, then 0C, 0D, 0E, 0F. Okay, so like this, you have total 8 locations here. Okay. Similarly, we have this one 8 locations here. So 0f is the that is 0f is in the decimal form, it is 15. So after 15 comes 16. 16 equivalent hexadecimal is 10. Okay, then comes the next address 17. 17 hexadecimal is 11. Okay, how to get, you just divide this number by 16. Okay, 16 1 are 16. So you see question one is remainder one. So it is 1 1. So I'll write 1 1. Then the next address is 18. So 18 again we divide by the 16 to get hexadecimal equivalent. 16 1 is 16. Okay, so I write 1 2. So here I write 1 2 in the hexadecimal form. So 1 2 1 3 1 4 1 5 1 6 1 7. Okay, so 8 locations here. Okay, this is register bank 2, this is register bank 1, then we have register bank 0. Similarly, here it was 16 plus 8 24, so it is 23. Now the next starting address of register bank 3 is 24 in the decimal. Okay, so in hexadecimal it is 18, then 25. In hexadecimal it will be 19 and so on. So 24 plus 8 is 32, so the last location will be 31. So 31 decimal hexadecimal equivalent is 1F. Okay. So like this we have total this first 32 locations. Okay, first 32 locations. Okay, they are reserved for register bank. Okay, so a better diagram is shown here. This one, see. So from 00 to the last address 1F. Okay, they are for register bank. Okay. Now total we have 128 bytes, out of which I just explained 32 bits, that is 32 bits or 32 bytes. 32 bytes. Okay. Another 16 locations. Okay. So from here to here we have 16 locations. So here 32 location means 32 byte, 16 locations. Okay, this is called bit addressable memory. Okay, this is called bit addressable memory. Now, just now I was saying you about something. These addresses were called byte addressable memory, which I explained you. Byte addressable memory. See, what is the difference between bit addressable memory and byte addressable memory? Is that here this 00 is the address of complete 1 byte. Okay, 1 byte means 8 bit. So here, whatever your data you are going to store, okay, so that will be affected by this byte address. For example, suppose that let's say I have written something like this: move 00h comma has, let's say, 12h. What is the meaning of this one? It is saying that in the address, this is the address. Okay, in this address, move this value of 1 2. So you see this 00 is this address which are shown in the bracket. In that address, 8 bit data can be stored. So in that case, 1 2 3 4 5 6 7 8. So this one will be written as 0001, and then 2 is 0010. So I think this was extra one. So like here this 8 bit data will be stored here, 0001, then 0010, and so on. Okay, so here the complete 8 bit data is getting stored here, and okay, each individual cells are actually stored with this 8 bit data. Fine. I'm saying that complete 1 byte of data will be affecting this location. Fine. But suppose in this bit address, what we are having is we are having both address. One is this 20, which is called byte address. Okay, byte address. So this 20 is the address of this complete location. Fine. This complete location is having the address 20. However, you see individual individual cells are also having some addresses 00, 01, 02, 03, 04, 05, 06, 07. Okay, so these 00, 01, 02 they are called bit address. Bit address, right? Why they are having, what is the application is that suppose that uh, for this particular you want that all bits should be, let's say in the address, okay, let's say in the address 20h, 20h, okay, you want to just in that address you can see we have bit address also. Okay, so this is 00 bit address, then we have 01 another address, then 02, and similarly the last is 07. Okay, so if you want to, let's say in only change some values in this address 00, so for that purpose we have instruction like set b. If I, what is the set b? Set b means bit, and set means 1. Okay, then we have another instruction CLR. Okay, CLR. So if I want to change this bit, okay, suppose that I want to store here binary 1. So I'll write set B, this address is 00. Okay, then I'll write comma, nothing else. Simply set B 00H. Okay, so by this instruction, this address 00 will now contain value of 1. Similarly, if I write CLR 00H, so by this instruction, this address 00 will contain 0. Okay, so this is how you can change the individual bit using the set and CLR instruction. Also, you will see that this is having some space. I mean, this is actually a specific feature of our 8051 microcontroller that we have here bit address. Okay, we'll see that where it is used when we will be writing some program. In that case, I'll show you. Okay, so here we have total 16 locations. Each locations have their own byte address. Okay, and as well as bit addresses also. Fine. So the in address 20, the bit address was starting from 00, it went to 07. In the next address 21, the again starting address is 08, 09, then 0A and 0F. Like this, it goes up to 7F. So up to byte address 2F, we have this 7F is the last byte address and this 00 is the first byte address. Okay. So we have seen the 16 bytes and 32 bytes, okay, out of total 128. Okay, so out of 128, we have seen 16 and 32 bytes how they are organized. Okay, that is 8 plus 48 byte we have seen. The remaining 80 byte, the remaining 80 bytes are called scratch pad RAM or general purpose RAM. Okay, so here we have another 80 locations. Okay, it, they are actually used for the general purpose. We can store this, I mean, we can use this 80 byte of RAM for some general purpose. Okay, for the temporary storage of data and so on. So this was actually the RAM organization of your 8051 microcontroller, 128 bytes. Okay, and moreover, you can see we have another here address ranging from 80 to this FF, okay, in which you are actually storing the address of different special function register. For example, this P0, okay, P0 is having this address. Okay, this is how again bit addressable also. Okay. Similarly, the stack pointer register address is 81H. Similarly, this data pointer register, which is 16-bit register, is having the address 8283, and so on. The TCON is a special function register. Okay, TCON is also special function register. TMOD is a special function register. They have their addresses 89, 88, and so on. Okay, so uh, so suppose that you are writing this tmod register. Okay, so tmod register, you can use, suppose that in the tmod register you want to store something like 15H, 15H. Okay, so you, what you will write? You will write the move instruction, something like this, move. Then you write this tmod, the name of the register, comma, as 15H. This is the one way. Okay. Then we can do in another manner. What is the address of this T mod? 89H. So I'll write something like this. Move in now 89 is destination. So I'll write here 89H, comma. What is the data that I'm supposed to store? 15H. So I'll write here 15H. Okay, this is another way. Okay, this is also another way. Because this T89H is the address of T mode. Okay, so you can use this one, which is called direct addressing mode. Okay, we'll see the addressing mode, and you can use this one, which is called register addressing mode. Not a register addressing mode. Here we have only one register, not this one. You can say immediate addressing mode. Immediate addressing mode. Okay. So this is about the 128 byte of RAM. Okay, then come back to our PSW register in which we have seen this RS0 and RS0. If you have, if you configure this 2 bit, okay, I recall I've already shown. So by coding them like 00, the register bank 1 is selected. Okay. By coding them as 01, you can select register bank 1. Similarly, by coding them 10, you can select the register bank. Okay, so like this, we can select the different register bank. So here we will see that how it is actually how the register banks are selected and the push pop instruction how they are executed. Okay, we'll see this in the next class. So today we'll stop here. So thank you everyone.